Recording. Good evening, everybody. Today we're going to talk about the respiratory system. Again, my name's Ann Lemaster, and I'm here for the synchronized sessions for APHY 102. All right. Oh, here we go. All right. The respiratory system consists of passages that filter incoming air. This is important because it's going to moisten the air, it's going to warm the air, and also it's going to remove any debris from the air. Transport it not only to the lungs but also to the body, and gas change will occur at microscopic air sacs called alveoli, and we'll talk about those in a minute. And the technical term for gas exchange, let's use the arrow here, is respiration. And gas exchange, usually we mean the exchanging or where oxygen and carbon dioxide are moving across cell membranes. That's usually what's meant by exchange of gases. The events of respiration include ventilation and breathing, and usually this is what most people think of when they think of respiration, but ventilation is just referring to inhaling and exhaling, okay? And that's the movement of the air between the atmosphere and the alveoli, and again the alveoli is a space in the lung. Well, let's try this. Erase all drawings and move here, and here we go. Okay, other important functions of the respiratory system is external respiration. External respiration is the exchange of gases between the alveoli and the blood. In other words, the pulmonary capillaries are going to gain oxygen and lose carbon dioxide. So again, remember the pulmonary capillaries are carrying the deoxygenated blood from the heart to the lung. So again, they're going to gain oxygen and lose CO2, so become oxygenated, if you will. There's the transport of gases. How are oxygen and carbon dioxide transported? And hemoglobin is the main transporter of oxygen, where carbon dioxide is the main transporter of CO2. Internal respiration is gas exchange between systemic capillaries, and by systemic capillaries we mean the capillaries of the body and tissue cells. So that's occurring anywhere throughout the body. So in internal respiration, oxygenated blood is going to become deoxygenated, meaning the blood is going to lose O2 and gain CO2. And lastly, the function of respiration is cellular respiration. This is how our cells make ATP. Our cells take oxygen and glucose and convert that to ATP and CO2. So if you ever wondered why we have to breathe in oxygen, right here, and why we breathe out CO2, it's because it is a waste product of cellular respiration. Creation of ATP, again, that's what cellular respiration does. And let me erase my drawings here. Okay. Again, why we breathe? Primarily gas exchange. And the two primary gases we're going to be talking about are oxygen and carbon dioxide. Again, we need it for ATP. And another aspect of ATP production is the production of CO2. Let's go to Spotlight. So here's this little equation. CO2 plus water is converted into carbonic acid plus then that can be converted to hydrogen ions and bicarbonate ion. And we've seen this equation before, but what this equation is referring to is how carbon dioxide helps to regulate our pH. So the respiratory system also provides oxygen, eliminates carbon dioxide, and helps to maintain the internal environment's pH. Okay. Upper respiratory and lower respiratory tract. Here's the pharynx. Again, we've talked about this in the digestive system. Anything superior to the pharynx is upper respiratory, and anything below the pharynx is referred to as lower respiratory. Now, functionally, you have what's called conducting zones. And think about a train conductor. It's directing the air from the nose to the bronchioles. So it's sending the air into the lungs. So this would all be conducting. The respiratory zone is where gas exchange occurs, and that's going to occur in the alveoli. And we'll talk more about the respiratory zone as we continue. All right, now we're going to get into a little physiology. No, that's not what I meant to do. The first aspect of physiology is why we breathe or why we ventilate, and the occurrences that happen inside our thoracic cavity and how that causes air to move in or out. Again, inspiration is causing the air to come in, and expiration is moving the air out. And if you take a moment and take a breath, if you inhale, you'll notice your thoracic cavity gets larger. And if you exhale, you notice your respiratory or your thoracic cavity gets smaller. And this kind of correlates with Boyle's law. And it states, Boyle's law, pressure of a gas in a closed container is inversely proportional to the volume of the container. What that means is the larger the surface, or the larger the volume, the more volume you have, the lower the pressure. Whereas the smaller volume, the higher the pressure. So again, this is how syringes work. When you pull the plunger back, what you're doing is creating more volume, that's lowering the pressure, and the fluid is going to move from high pressure in the container into the lower pressure. Whereas when you squeeze the plunger in, you're making this volume smaller, so this is higher pressure, and it will go to lower pressure, which would be where you're injecting the fluids. So air movement is occurring the same way. So our breathing, our inspiration and expiration, basically is changing the pressures in our thoracic cavity and allowing air to move in or out. So again, inspiration, first let's talk about atmospheric pressure, and that's just the pressure because of the air. And normally this pressure is around 760 milliliters per mercury. So when we inhale, okay, we're increasing volume and we're decreasing pressure. So we want our thoracic pressure to drop below 760 millimeters of mercury. That way air will come in. So when we inspire, when we inhale, we manage to drop our thoracic pressure to 758-ish. So when we inhale, and let me switch to the spotlight here. When we inhale, what we've done is made our thoracic cavity larger. That has dropped the pressure, and that causes air to move into our lungs. Okay, the main muscle responsible for inspiration is the diaphragm, and that's here. Now the main innervator, the main nerve that innervates the diaphragm, we'll go back up here, is the phrenic nerve. You might remember phrenic nerve when we talked about plexi, and there's a little rhyme, C3, 4, and 5 help keep the diaphragm alive. So the phrenic nerve is made up from cervical nerves 3, 4, and 5, and this is going to innervate the diaphragm. So this is going to tell you when to inhale. Okay. Inhalation, the most important muscle is the diaphragm. So it's going to contract or flatten. And this is responsible for about 75% of the air entering your lungs. During quiet breathing, about 500 mils of air enters the lungs. That's a little over a Coke can of air, if you will, or one like small water bottle. It's about 500 mils. This is also referred to as tidal volume. When you exercise, you can get 2 to 3 liters of air, so one bigger Coke bottle. Other important muscles for inhalation are the external intercostals. These are the muscles between the ribs. They're going to help elevate the ribs, and about 25% of the air entering the lungs during normal quiet breathing is due to the elevation of the ribs. Now, should you be exercising, other muscles that come into play are the sternocleidomastoid, the scalenes, and the pectoralis minor. Okay, all right, that's working. Okay. So again, when you inhale, okay, you contract the diaphragm, and that causes the pleura to adhere due to pressure and surface tension. Surface tension is the attraction of polar water molecules, okay? And you are going to pull the pleura, which is going to decrease interpleural pressure, and that's going to cause the lung volume to increase, and so the intrapulmonic pressure is also going to drop, and that's going to cause air to flow in. Okay. Expiration basically is just, expiration is also referred to as passive, but it's the relaxation of the diaphragm and elastic recoil of the lung tissue from surface tension. In other words, the lung is going to go back to its original shape. And when you inspire, or when you expire, your thoracic cavity gets smaller, and that's going to raise the air pressure above atmospheric pressure. So air is going to move from high pressure to lower pressure. So you're going to be breathing out when you expire. Okay. Okay, so again, expiration is passive because muscles relax, and elastic recoil of the chest walls. So your lungs have elastic fibers, and they are going to go back to their original length. Also, the alveolar fluid, the surface tension. Surface tension wants things to be as small as possible, so that's going to help the pleura return to its original shape. the diaphragm's going to relax, the external intercostals are going to relax, and again, that's going to increase the air pressure in the thoracic cavity, and that's going to cause the air to move from your lungs into the atmosphere. Now, during times of forceful breathing, you can also use your abdominal muscles and your internal intercostals. Okay. Airflow. Airflow is just which way the wind's going or which way the air is moving, and it is driven by pressure differences. And three factors affect airflow. One is surface tension. Again, surface tension is the attraction of polar molecules. And surface tension or polar molecules want to be as close as possible. So surface tension is important because it's going to help keep your villi in a nice round bubble shaped. But surface tension has to be overcome in order for the lungs to expand. Again, when the lungs return to their normal shape, that's about 2/3 of elastic recoil. Your lungs produce a molecule called surfactant that's going to help reduce surface tension, and this could prevent the collapse of alveoli at exhalation. In other words, if there's too much surface tension, the alveoli, which are kind of rounded, would get smaller and smaller and smaller until they collapse, kind of like a soap bubble. Gets smaller and smaller and smaller till it, well, pops. So you produce a molecule that keeps the alveoli nice and round and open. This is also what's given to premature babies should they have trouble breathing. Other things that affect airflow, lung compliance. Compliance is the ability to stretch. Again, this has to do with surface tension, but it also has to do with the elastic fibers. And anything that affects the normal tissue, such as scar tissue or high fluids, decreases lung compliance. Another aspect of airflow is airway resistance, and that's related to airway diameter. So the larger diameter, the less the resistance. You can think about drinking from a straw. The larger the straw, the easier it is to drink from the soda cup, as opposed to a coffee stirrer, which is smaller. And your body does have ways of regulating airway diameter. You have lots of smooth muscle, and you can dilate and constrict that. Control of breathing. Mostly breathing is involuntary. However, you don't have to think about it. However, there are moments when you can think about breathing, so there is a voluntary component as well. The main areas in the brain that regulate respiration are the medulla and the pons. Again, these are areas of the brainstem, and the pons kind of regulates the medulla. Other things that affect breathing, excuse me, are partial pressures of oxygen and carbon dioxide. Again, the term partial pressure is used. Remember, air is a mixture of things. It's only 22% of oxygen and about 0.3% carbon dioxide. It's primarily nitrogen. So that's why we use the term partial pressures. How much stretch? Emotional state. So your higher cortical levels can affect your brainstem and the pontine and medullary areas. as well as physical activity. Also, to help with the feedback, you have mechanoreceptors. These are going to be measuring the stretch of the lung and other the blood vessels, among other things. And you're going to have chemoreceptors. And anytime you have chemoreceptors, these are going to be measuring chemicals. For example, oxygen, carbon dioxide, and pH. Okay, so what causes air to move in and out of our lungs are pressure gradients. Now we're going to be talking about respiration. And what's going to be driving respiration, or the exchange of gases, is diffusion. Not only is it concentration gradients, but it comes back to pressure gradients. So oxygen and carbon dioxide are going to move from the lung to the capillary because they're going to be moving from higher pressure to lower pressure via diffusion. Okay, so a couple properties we'll see of the respiratory membrane, and we're talking about the alveoli and the capillaries, is they're very thin, and gas exchange is quick, and increased diffusion is favored with more surface area. So I've read somewhere that if you unfolded the lungs into 1 cell thick, the surface area of the lung would cover a tennis court. So surface area, the greater the surface area, the better the gas exchange. Again, shorter distances, you want thin membranes and partial pressure gradients. These are all going to affect the diffusion of the gases. Okay, here's a picture of the respiratory membrane. You have the alveolar wall. This is the tissue that makes up the lung. There's two types of cells. The simple squamous here, which is type 1. Type 2 is going to secrete surfactant, and again that's responsible for keeping surface tension at bay. There's a basement membrane, because all epithelial tissue is attached to a basement membrane. Then we're going to talk about the capillary. The capillary also has a basement membrane because it is composed of endothelium, which is simple squamous. And this is very thin. It's only 0.5 microns thick. So a micron is a millionth of a meter. So kind of like this picture. So here's the alveoli here. Here's this cell, simple squamous cell that makes up the alveoli, along with the basement membrane. Here's the capillary here, and here's your red blood cells. Again, capillaries are so small that red blood cells have to move through one cell layer, or one cell at a time. Again, that's going to slow them down and allow for diffusion to occur. Okay, so let's talk about external respiration. Again, it occurs in the lung, so I always associate the word external with where the air is coming from. In the lung, the air is coming from the oxygen is coming from the outside. So the oxygen is going to move from higher pressure in the alveoli to lower pressure in the capillaries. So 105 is alveolar air, the partial pressure of oxygen, whereas in the capillaries it's about 40 millimeters of mercury. Okay, and air is going to diffuse until in the pulmonary capillaries it matches the alveolar air, which will be approximately 100. In carbon dioxide, the deoxygenated blood has 45 milliliters of mercury, or millimeters of mercury, excuse me, whereas the alveoli has 40. So CO2 is going to leave the capillary and enter the alveoli. So long story short, in external respiration, deoxygenated blood is entering the lung. So carbon dioxide is going to leave the capillary and travel to the alveoli to be gotten rid of, whereas oxygen is going to leave the alveoli and enter the capillary. And again, here's where you have your deoxygenated blood, and after external respiration, you now have nice oxygenated blood. Internal respiration occurs throughout the body, and it's the reverse of external respiration. Oxygen is going to leave the capillary via diffusion, and that what driving the diffusion is pressure gradients. So it's going to go from 100 in the capillary to 40 in the tissue cells. So that means oxygen will leave the capillaries and enter the tissue, and that will drop, and that will continue till everybody's nice and copacetic. Carbon dioxide, again, will move from the tissues where it's higher to the capillaries where it's lower. And again, it will reach 45 milligrams of mercury, which is equilibrium. And here's a cool fact. At rest, only about 25% of the available oxygen is used. So deoxygenated blood retains about 75% of its oxygen capacity. And this is because in case something should happen and you need to flee or fight, you still have oxygen available to use. So here we're showing internal and external respiration, and we're corresponding it to pulmonary and systemic circulation. So we'll start here. Okay, we'll start at the alveoli. Here is external respiration, so blood is becoming oxygenated, and it's going to go through the left atrium to the left ventricle and to the body, and then internal respiration will occur, and the blood will become deoxygenated. It will return to the heart, to the right atrium, then it will go to the lungs after it leaves the right ventricle, and here we have the pulmonary circuit. Okay, so pulmonary circuit at the top, blood becomes oxygenated via external respiration, and at the bottom you have the systemic circuit, and blood becomes deoxygenated via internal respiration. And again, this is all driven by diffusion, and diffusion is moving due to pressure gradients. It's going from higher to lower pressure. So gas exchange depends on the partial pressures of the gases. Surface area, more surface area is better. Diffusion distance and weight. And remember, the diffusion distance is only about 0.5 micrometers. So how does the blood transport oxygen and CO2? Well, oxygen transport is all about the hemoglobin. Okay, so here notice the chemical bonds between oxygen and hemoglobin are unstable. You want unstable bonds so hemoglobin can bind, and also it can let loose of the oxygen. And here we're just showing, we're kind of going over external and internal respiration. And again, what's carrying the oxygen in the blood is hemoglobin. So here's oxygenated hemoglobin in external respiration, and here in internal respiration you get the deoxygenated hemoglobin. Here is our friend the saturation curve. And here you have the percentage of saturation of hemoglobin, and here you have the partial pressures. So remember, at rest, deoxygenated blood is 75% saturated. So if you go to 75% here, so I'm going to 75% here, and notice that's about 40 millimeters of mercury. When the blood is 100% saturated, okay, coming up to this soon, its partial pressure is around 100. So this is showing you the saturation of oxygenated blood, and here at the 40 is the saturation of deoxygenated blood. And what the next couple of charts are showing you, again, is what factors affect how hemoglobin will release oxygen. The first one we're going to talk about is pH. Remember, pH corresponds to CO2 levels. So the more CO2, the more acidic, or the lower the pH. And why this is important is because that means when the pH is low, your saturation curves are moved to the right, so more oxygen is being released. So deoxygenated blood has about, 55% saturated hemoglobin. Now, if you look at partial pressure of CO2, and here's my mouse, when the partial pressure of CO2 is higher, which is the brown, when blood is deoxygenated, it's about 50% saturated. So the more carbon dioxide in your blood, the more hemoglobin is going to let go of the oxygen. And lastly, another factor that regulates how hemoglobin binds to oxygen is temperature. And here we're going to look at 43 degrees Celsius. This is indicating that you are probably exercising. So again, at 40, when blood is deoxygenated, notice that it is containing less oxygen than at rest. Because again, if you're moving and exercising, you're probably using more oxygen in order to keep up all your metabolic reactions. Now, carbon dioxide transport is a little, well, there's 3 parts to carbon dioxide transport. In other words, there's 3 ways your blood carries carbon dioxide. Carbon dioxide can dissolve in the serum or in the plasma, and that's about 7%. About 23% binds to hemoglobin, but it's binding to the amino acids in the hemoglobin, not the iron molecules like oxygen. And the other 70% becomes bicarbonate ion. So the bicarbonate ions are formed in the red blood cell, and then the bicarbonate ions diffuse out of the red blood cell and go into the plasma. And what this picture is showing you, again, is how carbon dioxide is carried in the blood. So when the carbon dioxide, again, this is internal respiration, leaves a cell, about 7% can diffuse directly into the plasma. 23% will bind to the amino acids of hemoglobin. The other 70% will combine with water and be converted into bicarbonate ion. And bicarbonate ion will leave the red blood cell and go into the plasma. Now, lastly, we have the chloride ion shift. The chloride ion shift is referring to the fact that to keep the charges similar in the red blood cell, remember, bicarbonate ion has a negative charge. Let's go down to our picture here. Bicarbonate ion has a negative charge, and it's going to diffuse. This is the red blood cell. Okay, bicarbonate ion is made in the red blood cell, and it's going to diffuse out into the plasma. Well, to keep the charges equal, chloride ions will leave the plasma and enter the red blood cell. So you keep your charges nice and equal. And this is referred to as the chloride ion shift. Now, in external respiration, well, let me see. Oops. Let me get rid of my arrow here. Okay. In external respiration, CO2, about 7%, is dissolved in the plasma, so it just diffuses into the alveoli. 23% has bound to hemoglobin, so hemoglobin is going to release that, and it diffuses into the alveoli. Now, the bicarbonate ion is going to re-enter the red blood cell and be converted back to CO2. Then the CO2 is going to diffuse from the red blood cell to the alveolus. Another factor that's not shown here is the chloride ion shift. When the bicarbonate ion moves into the red blood cell, then chloride ion will move out, again to keep the charges equal. And here is a very nice graph to help you review what happens when, or to review how gases are transported in the blood. Well, that's all I have for you this afternoon, so thanks very much for joining me, and thank you.